So let's start electricity. Now we will quickly do revision of electricity. This is a revision. So first of all, the theory of the electricity, that is when there is a circuit, let's say there is a wire, let's say there is a conductor wire, and when we apply some potential difference across it, when we connect a battery to this circuit, this wire, this conductor wire, then what happens is that there are some positive charge here, there are some negative charge here. These charges these charges have some potential here, and these positive charges will push away the positive charge, or you can say that they will attract the negative charge here in this direction, and this will repel the electrons away from it. So in case of conductors, they have only electrons which can move, electrons only which can move. In case of conductor metal, in case of metallic conductors, so means a solid conductor, we are talking about a solid state object which is a conductor of electricity. In those things only electron is able to move, and the positive charge, which is the kernel, whatever we call it, that is always rigid, fixed, and only electrons are free to move. Conductors have free electrons which can move and produce current, while insulators they don't have free electrons. Conductors have free electrons, but insulators don't have free electrons. These free electrons can be easily forced to move by applying some electric field. So when there is a conductor, let's say this is a conductor and there is some electron inside it, these are free electrons, and when I apply some electric field, what happens is that these electrons will move in the opposite direction of electric field. Now we have heard that in conductor field E becomes zero, but that happens only in electrostatic case. So unless this electrostatic situation is achieved, we will not see this. This will only happen when this will happen. This electric field will become zero inside the conductor only when the electrostatic condition is reached. But if the current is continuously flowing in this conductor, then there must be some non-zero electric field. If this is not given, if this is not the condition of the charged particles. So if the charged particles are moving, then for sure there is some electric field and they are accelerating with some force. Force acting on the electrons would be E into E, and these electrons will move in this opposite direction of the field, and this is how the motion of electrons starts. And in case of a very long wire in which we connect it with a battery with positive terminal and negative terminal, what happens is that when there is a wire like this, let's say this is a wire and I connect this to with it, then what happens is that this positive charge from this starts distributing. There is some redistribution of charge. There is redistribution of charge all over wire. So how it happens is that there is large positive charge in this side, there is large positive charge at this side, and then it starts decreasing, and here there is large number of negative charge, and it decreases, and there is any point here where the charge is zero. So here the surface of the these are the surface of the wire. The surface of wire has some charges accumulated. Surface of this conductor will accumulate some charge over it, and similarly at the negative side there will be some negative charge accumulated. And these two, since there is large positive charge here and small positive charge here, this will cause the net electric field in this direction in the wire. Similarly, here it is less negative charge and here it is more negative charge. So electric field will point in this direction somehow, because at this length the electric field would be in this direction, and the electric field due to this charge would at this point would be in this direction, and the electric field due to this charge would be acting in this direction, but their magnitude is less, therefore their electric field is less. Means if I take a straight wire and I say that it is connected with a positive terminal here and there is another terminal negative here, and I connected it, so what happens, there is more positive charge here, then less negative, then less positive charge, then it becomes zero somewhere, then negative, then more negative, then more negative charge. So what happens is that these charges are accumulated at the surface. This is the surface of conductor. So this field will cause, this charge distribution will cause some field in this direction, and this charge distribution will cause some field at this point in this direction. Since this is larger in magnitude, so this electric field, the direction of electric field net would be in this direction, because this is greater than this, so it gets cancelled out and in net electric field in this direction. And similarly it happens, it keeps going on in the with means this process keeps going on ahead, like this is more positive charge, this is less, so the electric field will be in this direction. This is more positive charge, this is less, then again in this direction. This is less negative charge, this is more negative charge, this will cause the electric field in this direction. Like, because let's say this causes some very large electric field in this direction and this causes little electric field in this direction, so the net electric field will be in this direction. So somehow this distribution of charge in the wire causes an electric field to form. Even though the shape of wire is like this loop, but still due to the distribution of charges in the wire, the electric field in the wire is along the wire, like this. The electric field is along this path of the wire. So this is how the electric field is generated inside the wire. And when the electric field is generated, once electric field is generated, the next step is that the electrons will experience a force. If there is an electric field, then the electrons will experience a force minus, if that is a force on the electron that is experienced by electron. This is E into charge of electron, and now the acceleration of the charge would become simply E into E minus by mass of the charge, mass of electron. So this becomes the acceleration of the electron, and when we calculate the drift velocity, there is some acceleration of the charge. And in case of conductors, we know that in conductors there are positive charges or some negative charges in the medium. There are some positive rigid cells, positive rigid charges which cannot move, and some free electrons. So when an electron moves in this medium, sometimes it gets collided by another electron or any positive charge, and it loses all its momentum. So the momentum of the electron is lost after it collides with any atom or electron. So in such cases, we have to take care of the time up to which this object is accelerating. So it is not a fixed value. Different particles will collide at different times. Let's say this particle first collided after t1 time, then it collided after t2 time, then it collided after t3 time. So the collision may be happening after some t1, t2, t3, some different times. Then the mean of these time values of collisions, the time before two successive collisions, if we take the mean of it, then it is called tau, which is called the mean relaxation time. Mean relaxation time means the time between two successive collision, mean of that value, the average value of the relaxation time. So in such cases, when the particle is assumed to be accelerated only for tau time, then we can say that acceleration into tau is equal to the change in velocity, which is v, and this becomes this it is equal to final velocity, and acceleration is equal to minus e into tau over m. And now in this case, this we will take as the formula of drift velocity. Well, if we see clearly here, then we will see that this is the final velocity, and drift velocity means the average velocity by which electrons are moving. So this is the final velocity, and the electrons started with zero velocity. So it means the average velocity should be equal to v final plus 0 over 2. It means the v average velocity, that is equal to v drift velocity, should be equal to minus e tau over 2m. But we don't take this value 2 in NCERT. We don't take this 2 value. In some books there is this 2 value, in some books it is not, but according to the NCERT, we will not take 2 here. So we will not take the average, we will simply take the v final velocity we have calculated for the v drift. So this will be the formula. And it is also said that we don't actually know the behavior of the electron flow inside the conductor exactly. So this factor of 1 by 2 or 1 by 3 or something else, this doesn't matter much. That is why we ignore that extra coefficient, and we only take care of the variables, and we remove all the constant values from the equation. So that's why the drift velocity becomes simply e tau by m. And the sorry, we are talking about average velocity, so this will become e into e tau by m. And if you want to write the direction of the drift velocity, then we have to write v drift velocity is equal to minus e tau, sorry, minus e into e tau over m. This becomes a drift velocity. Simply by acceleration into time, we get its final velocity, and we simplify to get the average velocity. This is the average velocity, but average velocity should have two value here, but it is not that simple to predict about the motion in case of, I don't know, but in NCERT this is the formula for drift velocity. That's it. This is still a confusion if it is 1 by 2 or not. In some books it is, and in some books it is not. So it's better to go with what is written in the NCERT book. Now moving ahead, we have found the drift velocity. Now the current value. There is a conductor, let's say it has cross section area A, and the electrons are flowing with a drift velocity d, and the density of electron, let's say n. It means let's say there are n number of electrons per unit volume. This is the number density, the number of electrons per unit volume. So what happens is that we will to find the total number of electrons in a small area. Let's say this is dx area, this is dx length, and this is a area of cross section. Then the volume of this small part is dv is equal to dv, and dv is equal to dx into a, and the number of electrons flowing in this is dn is equal to n into dv, which is equal to dx into a into n. Now the time taken for this is small number of charge to pass through this line, this point, is vd dx by v. This whole part, this whole length will pass through this point in v dx by vd time. So the time taken is dx by vd, and the total charge passing through it is equal to q is equal to number of electrons, which is a into n into dx, and multiplied by the charge of electron, and the time taken is dx over vd. So we get the formula of current is equal to q by t, which is equal to a n dx e over dx into vd. So this gives n e a vd. So the formula of current becomes n e a vd. So what is current? Current is the amount of charge passing through a point. In how much time does it pass from a point? Let's say there is a charge, nothing, just this, just remember this, the rate of flow of charge, that is the current. Now this was the formula of current in case of drift velocity given and number density. Now there is one other term which is called mobility. Mobility is simply defined as mu is equal to E upon vd per electric field, drift velocity per unit electric field. Whenever we know that the formula of drift velocity is equal to E a tau over m, so the value this part, this is called the mobility E tau by m, where E is the external factor and this is the factor of material. This depends on material a lot, and this depends on the external source of electric field, which can be right. So mobility is the property of a material, and mobility I think, okay. So now Ohm's law is simply says that if there is some potential difference V across this circuit, if let's say there is V potential difference across 2 points, then there will be some current flowing in this wire. Let's say this is higher potential A and this is lower potential B. Then there would be some current flowing from there would be electric field pointing from higher potential to lower potential, and the current will also flow in the direction of the electric field, because if the electric field is in this direction, then electrons will move in this direction, and if electrons move in this direction, we can say that we can assume that the positive charge is moving in this direction. Negative charge moving in this direction is equivalent to the positive charge moving in this direction. So we can say that the current is flowing in this direction of electric field. And now if there is a potential difference between A and point B, then there will be some current flowing in this wire along the direction of electric field, which is I, and the resistance between A to B is R. So this would become the Ohm's law. We know that, and this R is given by rho L by A. where this rho is the resistivity and L is the length of the wire and A is the cross section. If it is a uniform, if it is a uniform wire, then we will use this formula. And if in the series, this is A to B series, in series, if these values are variable, then we will have to take the sum of all dr vectors to give the R equivalent, which means we have to take the integral of rho L by rho dx by A into what? That's it. Rho dx upon A. Integration of this from A to the B. And if the wires are connected, if there are many materials connected in parallel. So in case of parallel, this was for series. In case of parallel, we will take 1 upon R equivalent is equal to integration of 1 upon dr, which is equal to 1 upon rho dx, rho x length would be same for all, and this would become dA. Now we will take the integration along the area, and the length would be constant, taken constant. So this is how we will calculate the resistance in case of parallel, and this is how we will calculate the resistance in case of series. So this was on rho and all. Now the value of rho is given as m over n e square tau. So rho is the tendency of the material to oppose flow of charge. Rho opposes flow. This rho value of resistivity opposes flow of electrons, or we can say charge. So rho opposes the flow of charge, while R, there's a difference between resistivity and resistance, and the difference is that rho resistivity opposes the flow of charge and R opposes current. So R opposes the current, while current and the flow of charge both are not the same thing. Let's say there is electron here moving with a small velocity, and I add one more electron here, and it is also moving with the same velocity, and I add more electron. This current will keep increasing as I increase the area of cross section. So this is what resistance is about. It depends on area of cross section, and the resistivity, it does not depend on the area, depend on area of cross section, and it actually opposes the flow of individual charge. So in this case we will say the current is increasing, therefore the resistance is decreasing, but in this case resistivity is still same, because the the difficulty by which this electron would be moving is still same. These are some formulas, and now moving ahead. So rho is equal to m mass. The more is the mass of the electron, the lesser is the velocity it would gain. The density, the lesser the density, the lesser number of electron, the lesser number is the lesser current. The lesser is the amount of charge, the lesser is the current. The lesser is the time, the lesser is the speed. So overall, these all help in current, like we have seen in any AVD, where VD is directly proportional to time, and this is any A. So current is directly proportional to these quantities. That's why resistivity is inversely proportional to them. Now what happens next is that the another formula is that we have V is equal to IR, and there is one formula for current. We had one formula which is equal to NEA BD, and I can also write current is equal to J dot A vector. If there is some current density, there is current per unit area. This is the current per unit area. So if I take the integration of current per unit area, I integrate for whole surface area, for whole cross sectional area, then it will give the total current passing through it. So this is another way of finding the current density, current from the current density. And current density, so there is one law of that is like equation of continuity, an equation that is similar to the equation of continuity, that is a1 v1 is equal to a2 v2. So if the velocity of the electrons at any point is, let's say, v1 and area is a1, then in series if there is another area of cross section a2, velocity v2, then we will have this condition true, because a1 v1 is the current value is equal to NEA VD. Since this is a constant value, this value must be constant all over the series, because current is always constant all over the series. If current is different, let's say this is a wire, and if current is different, here it is lesser and here it is higher. So what would happen is that if current is higher at this point, there would be more positive charge coming out and negative charge will start accumulating here, and it will give and will start pulling the positive charge in this direction. So that's kind of not gonna happen. Accumulation of charge does not occur in case of current in conductor. Accumulation charge in complete circuit doesn't happen. So if there is current flowing, there would be no accumulation of charge. You can say if current flowing, there would be no accumulation of charge in case it is flowing in a complete circuit. And next is first thing about the resistance, or let's say the resistance of the body can be written as R naught bracket 1 plus alpha delta t, where alpha is the coefficient of, I don't know, temperature maybe, that is the resistivity coefficient of temperature. Maybe we can write rho is equal to rho naught bracket 1 plus alpha delta t. So this is the formula of resistivity. And the graph of some materials resistivity looks like this. For a normal metal, this graph is curvy, and at the 0 Kelvin temperature, this is on the Kelvin scale, at 0 Kelvin, the normal metals have some resistance which is very small, but they have some resistivity and some resistance. But alloys are made in such a way that they follow this directly proportional relation, so their graph of resistivity becomes straight. As with the temperature, their resistivity also increases linearly. And in case of semiconductor, the resistance at zero temperature is infinity, because in such cases you cannot produce any current in this. So at 0 Kelvin temperature in superconductor, there is no current produced inside the superconductor. Its resistance is assumed to be infinity. That's why, because we cannot produce current in it. Then